Hello everyone, I'm Hermès McGriff and I'm presenting the paper I have written with Renato Martins, Nicolas Andreff and Cédric Demonceaux entitled Joint 3D Shape and Motion Estimation from Rolling Shutter Light Field Images. The main contribution of this paper are first, a generic projection model of rolling shutter light field cameras, second, a new linear bundle adjustment strategy to estimate jointly the 3D shape and motion in such a setup, and third, a new dataset of synthetic rolling shutter light field images paired with ground truth depth. The rolling shutter light field setup is the fusion of two setups, the rolling shutter setup and the light field setup. The goal of this paper is to leverage some specificity of each world in order to solve a new kind of problem that is capturing 3D shape and motion in only one picture. On one hand, the rolling shutter setup is sensor dependent. Most consumer cameras are equipped with a rolling shutter sensor that exposes its pixels line by line. That means that all the pixels are not capturing the same moment in time. When the scene moves, it can appear what is called the rolling shutter effect, and the scene seems deformed. On the other hand, the light field setup is an optical system. To make a light field image, we can put a microlens array in front of the sensor of a classical camera. It creates something like a multitude of well-organized little cameras. This setup is commonly called a light field camera. We can also acquire a light field from an array of cameras. It allows you to do a very compact multi-stereo and to compute depth from a single image. Now, what happens when we have a scene in motion in front of a light field camera equipped with a rolling shutter sensor? We first initialize a deformed point cloud with classical multi-stereo. Then, we optimize abrupt projection error in a bundle adjustment strategy in order to compute a global velocity and to recover the 3D initial positions of the points detected. We have designed a rolling shutter light field projection model in order to describe the projection of a 3D point in such an image with respect to its initial 3D position and its 6D motion. In order to evaluate our method, we created the first dataset containing rolling shutter light fields. We compared our methods with state-of-the-art techniques for depth estimation from light fields. These methods, as they don't consider the rolling shutter effect, suffer from it. We show that our method is able to disambiguate the shape and the motion of the rigid scene, even in case of extreme velocities. Our future work will focus on densifying the point clouds and exploring non-rigid scenes and non-constant velocities.